All right, here we go. Oh no, stack tests. So 2 Prop Z is number 6. At least on mine it is. And then you just gotta fill in what you've got. Fill in what you've got. I called 1 the guys and 2 the girls. It doesn't matter, especially with the two-tailed test. It really doesn't matter. But it doesn't even matter if you switch the guys and the girls as long as you keep track of who's whom. All right, so 3 out of 10. Is 3 out of 10 any significantly different than 5 out of 9? I don't know. That's the point of the confidence intervals. Here we go. Look for area. Something's being graphed besides that curve. I know. Hang on.
Yeah, my phone. Let him do it.
I've got something else on. That's what I've got. I got too much stuff on. There we go. Here it comes. All right, what do you say? 55% is way bigger than 30%. Yes? Yes. But is there a significant difference based on this data? No! It does not appear there's a significant difference. Laura, go.
My calculator won't let me do it.
Oh, and the same thing happened to mine. Everybody, if it's not letting you do anything, press the on button. It should say break when you do that.
On?
Just the on button? Does it say break or anything?
No, I had too many plots.
So do this. Press the y equals button. And clear everything if there is anything out of y equals. Sometimes if you and turn your plots off. If you have your plots turned on, I had 2 equations and a plot, and that was confusing the hell out of it. So
I had like 3 plots.
cool. There you go. So the big takeaway. Let me know if that works, Laura. Okay.
Okay.
And the big takeaway from this is, and this is why you need to pay attention to things like sample sizes, is yes, 55% is a larger percentage than 30%. Of course, it is. Obviously, it's very large. The problem is, of course, is that in a sample size as tiny as the ones we have in here, there's so much random noise you have to allow for. Now, technically speaking, and I wouldn't ask you guys this on the examining class on Monday or on whatever day it is, Thursday, because it's too tedious. We didn't even satisfy the assumptions for the test with samples of size 10 and 9. Remember the n times p equaling 5? We were nowhere near that with 10 and 9. We've got far too few data points to actually do this. So what would you have to do in this case? This is why the last question of your outer class exists. You'd have to go find a non-parametric test to run. One that doesn't assume that it's... That bell curve right there? What we have demonstrated is the bell curve tells us it's inconclusive. But a better answer to this question, not the one I would expect on Thursday, is you shouldn't even run this test because you didn't satisfy the assumptions for it. If it was 30 students out of 100 and 50 students out of 90, that's a different story, isn't it? That's a different story. That's a more meaningful 55% and 30%. This is kind of like, to give you an extreme example, it's like asking the first 2 students to walk out of the room. Are you taking classes at COCC next term? One kid says no, one kid says yes, and you go and tell the board of directors, 50% of the kids aren't coming back next term. That's essentially what this is. This is a more innocuous case of. With that little tiny data set, little tiny fluctuations make a humongous difference, but those little tiny fluctuations are just random fluctuations. So you don't want a random fluctuation influencing the overall data set. You want the baseline of the data set influencing. Laura, did it behave for you now?
Yeah.
Okay, good. Does that make sense? You guys see what I'm saying? So I mean, I'll obviously find you better data sets. I'll find you ones that have more than 19 points in them, obviously. But just so you know, in your statistical worlds outside of this room, you'll run and get non-parametric tests to run instead of this. And you have part of your out-of-class exam is going and researching which ones they are.
I was going to say,
that's part of your...
we're not doing that.
No. If I gave you this data set in class, you would do exactly what we just did. Right?
And come to a conclusion.
And come to a conclusion. The conclusion is there's no difference.
Right.
The conclusion is there's no difference. That conclusion would change with larger samples, assuming percentages were maintained, of course. But yeah, you would just finish this off and call it good. This is just intro to prop stat 2. You get all the nuts and bolts.
Is there ever like a situation where you just multiply it by something, so each number by the same thing to get a bigger number?
That's a fantastic question. Why don't we just multiply everything by 10? You're assuming that, remember I mentioned that the random noise of 3 and 10? You're assuming that if I ask 10 times as many people, I'm going to get the exact same percentage of results. That might not be true, especially with teeny tiny data sets. Think about it this way. When you guys cracked open your bags of M&Ms and counted them, did you all get roughly the same number of each color in each bag? Hell no, you didn't. Do you remember our graphs up on the board? They were bell curves. Most of you got an average, near an average number, but they were about 10 different numbers wide. So you can't just say, okay, 1 in 10 was this, I want to get that many. Not necessarily. That might be closer to center or more of an outlier. So that's you can do that, you just shouldn't do that.
Right.
Yeah.
That's what I thought.
And I do it in class sometimes to illustrate things like margin of error, where I'll change the sample sizes to 10 or 100 times bigger. And we can keep doing it until there's significant differences. But the problem with doing that is, I'm assuming that they're going to stay centered at 30 and 55%, which might not be true. It's most likely assuming a random sample, which you guys sure aren't. But it's not good statistics practice just to invent data that's not there. Laura, go ahead.
So, if the question was, are more males driving 5 miles than females?
Excellent question.
For the, I'm just pulling up the mix.
Good for you.
Would you switch the P1?
Yes, you could. You could totally do that. We're recording, yeah. So Laura's question is, suppose we didn't phrase the question until we looked at the data. So suppose instead of saying, is there a difference, I asked you guys and you go, oh my goodness, over half the girls are driving more than 5 miles, but only a third of the guys are. That looks like the girls are driving more mileage than the guys, yes? The girls are driving more mileage than the guys. So then you would switch the sign. Now, you could switch it either way. You could phrase that as the girls are driving more than the guys, or the guys are driving less than the girls. And it doesn't matter to me which way you put it in, as long as you know which way you've put it in. So in other words, the test statistic that we got originally is going to be the same. You're still going to get a negative 1.12 no matter, or 1.13, no matter how you put it in. And this p-value is 26% right now. What's it going to be if you make it a one-tailed test?
13.
It's going to be half, or 13. It'll be 13%, not 26%. You can run the test again to see that, of course. But the thing is that you might not know it's going to be 13%. You might inadvertently get an 87% p-value, which means you put the sign in the wrong way. So in other words, using the way we've defined the variables right here, with P1 being the guys and P2 being the girls, it would be P1 is less than P2, or P2 is greater than P1. Either one of those is fine. It means the same thing. I think the TI makes you ask it a certain way, though. Hang on, let me look real quick.
Well, yeah, I think it's always P1.
It's P1, right? So we have to go P1 is less than P2 to get it correct in the TI. But if you define your variables as P1 was the girls and P2 is the guys, then it's going to be greater than. And the test statistic gets switched as well. So the fact that it's negative means we know the guys are coming first because they're smaller. Is that fair?
Yeah.
So your choice, and I know that looking at the exam. I just look for the absolute value, whatever number you got, and make sure that's right. Answer your question, my friend? Awesome. And here's the result of the test if you want to crunch it out. You're going to see there's your left tail, looks like similar to the last one, and now the right tail's gone. Half the p-value, same exact test statistic. Perfect. Perfect. Good. I asked you guys earlier if you knew your height to the nearest inch. Do you guys know your drive to the nearest mile to get here? No, not necessarily. Okay, just know it's more than 5 or less than 5. Okay, so I was going to maybe test how long our drive is to the nearest, see if the guys were different than the girls. But that's kind of dumb. We kind of know it's going to be most likely just because the girls are driving longer than the guys. It might not be statistics, but... So let's do our heights. Let's 65 miles. Well, there's an outlier. Very cool, though. Very cool. You're also one of the reasons I'm designing these hybrid courses. Yes. So let's change the question. Let's change the question. I've often been told, and the U.S. Department of Health and Human Services tells me this, that guys are taller than girls on average. That's just what I've been told over and over again. Guys are taller than girls on average. So let's test it in this class. Let's see if that holds up in this class.